right, welcome, ladies and gentlemen. This is the Georgia Tech AI podcast. Today, I have the pleasure of introducing a guest who's actively working on pushing the boundaries of sustainability and engineering, Rishabh Goel. Rishabh's work focuses on battery-free technologies and embedded systems. He's one of the key minds behind Protean, a platform that enables battery-free sensors to perform machine learning tasks in the midst of unpredictable energy conditions. His recent work is on battery-free UAVs, unmanned aerial vehicles, that's inspired by bird flight. So imagine a drone that's capable of flying the skies on ultra-long missions without the need for batteries. Rishabh's also ventured into healthcare innovation with phantom organs, most recently a phantom lung. So I'm thrilled to dive into his journey, his mindset, and also what drives him to tackle such diverse problems. So without further ado, please join me in welcoming Rishabh Goel to the podcast. Rishabh, it's great to have you here.
Hello, good to be here.
So before delving into your specific research, could you talk me through what your rationale is when you pick projects and decide what you want to tackle?
It's kind of simple for me. I just do things that I think are interesting and I'll have fun doing. And usually that ends up being something I'll learn a new skill or solve a new problem or tackle a new problem in an interesting, different way. And that's usually it. It's usually just I have a lot of ideas, usually. 99% of them are dumb ideas, but then I just end up working on things that I think are fun, and some of those things end up working.
I also see this overarching theme of sustainability and wanting to make things better. So is that part of you picking an interesting project?
Yes, definitely. I think sustainability is a big driving force for me. I'm always interested in how to make things last longer, but also how do we capture energy around from our surroundings or our environment in a more meaningful, useful way. Because there's a lot of energy available in the environment that is often overlooked or not used, and we end up burning fossil fuels or using batteries, which also have toxic chemicals in them, which have all these adverse environmental impacts. So I'm trying to figure out if there's ways we can make everyday devices or everyday objects more sustainable by harnessing the energy around us.
And what is the project that stands out to you that perfectly embodies this?
Well, one of the ones I'm working on right now is probably the battery-free UAV project, in which I'm trying to combine existing drone technologies with a completely battery-free system. So we're essentially trying to push the limits of flight as well as energy harvesting by hopefully creating a drone that can take to the skies and fly until the sun is out. And that should enable a lot longer flight time, but also a lot longer missions that weren't possible before, for everything from environmental monitoring to monitoring wildlife and volcano activities to city air quality monitoring and other applications of the sort.
And so what's the current state of the art with drones? To the best of my knowledge, we use lithium-ion batteries. Why is that a problem?
So the biggest problem with lithium-ion batteries is, without even getting into the environmental impacts, using them in a drone setting, one, they are they're pretty heavy, but they're still one of the better sources of energy we can have for energy storage. So they're used in drones as a simple way to essentially give drones energy to be able to fly for a certain period of time. The main drawback with them is that there's twofold drawback. One is due to the way batteries are, the more you use them, the more they'll degrade. And that degradation is actually also proportional to the amount of current you draw from your battery. And turns out flying drones and drawing those motors draws a lot of current, which ends up being that the batteries start degrading after a long time and after some time, and they end up needing to be replaced if you're doing any sort of industrial operations which require constant use of drones. So they end up getting replaced very frequently, which is not only a financial burden, but it also harms the environment because most batteries, especially lithium-based batteries, are pretty toxic to the environment and are hard to recycle and dispose of safely. And the other issue is just we were trying to essentially think of if we can create a drone that's efficient enough in which we can fly with the energy harvested from the environment, then why do we need to rely on a battery? Or so that could also potentially lead to down the road of creating a fully sustainable and biodegradable UAV in which every part of the system, including the energy storage, which making batteries biodegradable is pretty hard. But if we can just rely on biodegradable solar panels and wind energy harvesting, then we could create a fully biodegradable UAV that can fulfill its mission, crash into the soil, and just degrade. But that's more of a dream at this point.
Yeah.
Yeah.
So talk more about that. Why is it a dream? I looked at the results and it stayed afloat in the air for a bit and then it crashed. What's stopping you from doing this?
I think currently a lot of it is just funding. We've applied for some funding and we're still waiting to hear back. But I think just the whole process of trying and looking at different materials to build the drone out of and looking at different sorts of energy harvesting modalities or solar panel chemistries, and also how big the UAV needs to be to one, carry a payload, but also sustainably fly. It's an engineering problem with a lot of design constraints, but also a lot of variables that we can tweak, and they're all interconnected. So just studying that entire design space is very challenging and time consuming, and we need a lot of money, but also a lot of just time and engineering resources. Like a big thing right now is, funnily enough, we don't actually have an aerospace engineer on our team. This was all just done with me and a couple of my colleagues. We're all mechanical engineering or electrical engineering, and we kind of just learned on the fly how to do things and built drones. And so I think it's a little bit of just time, money, and more getting people with the right knowledge. Because making drones, especially flapping drones, which was one of our battery-free UAV prototypes, pretty hard.
Yeah, and like you mentioned, it's not just one specialty here, but there's so many skills that have to come together. Why flapping wings? Why that particular modality?
So flapping turns out to be a pretty efficient way to fly, which is kind of why nature evolved that way. But going into some of the reasons we chose flapping is it kind of gives us a nice balance between power and kind of between a high power mode in which we're flapping and producing lift and thrust to propel our bird forward. But if, for example, you have cloud cover, or if you need to go into a low power mode for either energy constraints of coming in, or if you want to do sensing and you want to record a lot of data. In either of these cases, you want to go into a low power mode, in which case you can just spread your wings and glide and kind of soar in the air. And that enables us to kind of have a good balance between maneuverability while also having a system that can actually fly stably. But also turns out flapping wing ornithopter control is a very hard problem. So in some of the initial tests we've done and the paper we published a couple years back, we actually never ran into a situation where we ran out of energy and crashed. It was always just instability in flight and controls. So that's something we're trying to fix with some more experiments and also trying to find some people who could help us with that problem.
Could you break down the difference between a downward flap and an upward flap?
So a down flap is essentially when the bird goes from the highest swing position to the lowest, producing lift and thrust. And an up flap is when the situation is reversed, when you're essentially going back to the upwards position. And it's very interesting because the way birds flap, there's two ways that actually mitigate the essentially downforce that's created when you do an up flap. So if you think about it, when you do a down flap, you're actually pushing the air down and creating lift. And doing an up flap, it's usually the opposite, which is a big problem we ran into. The way it's combated in nature is with feathers and with angles of the wings. So feathers play a big part in essentially they kind of overlap and create a solid plane when they're in the down flap. But in the up flap, they kind of separate and let air flow through to reduce drag, which is a very interesting thing. Turns out making that system in a very low weight, low energy sort of way is pretty hard and challenging. Some people have attempted it, but it always leads to systems being very bulky and just you can't really use the systems to fly, especially if they're not a battery-free UAV. And another thing birds use is actually just changing the angle of the wings. So a flatter angle when you're flapping down and a more steeper angle to let some of the air pass through when you're flapping up. We have attempted to do the latter with mixed results. We are at a point right now where we do produce more lift than downforce, so we can actually fly. But it's still a lot of downforce that we're creating. We're trying to solve. We have a couple ideas on how to solve it that we still have to test. I'm not going to talk about it. Okay. But yeah, we have. I've brainstormed a bunch of ideas with my other collaborator, and we are going to test some things and hope it works next semester.
So there are two areas that I want to cover. One is the materials, and the second is the energy storage.
Mm-hmm. With
the materials, how do you decide the materials that the wings will use and the frame will use? What was the rationale?
The idea behind, or what we thought of, was essentially the biggest factor is we will have limited lift to play with. So at least for the body, it was a pretty easy decision of we need to create something robust enough to fly and withstand a few crashes, but also light enough that it can actually fly reliably. So we ended up going with carbon fiber because just one of the best materials in that respect. But for the wings, it was a much harder problem to figure out what to put on the wings. Initially, we even thought maybe we should make the wings out of solar panels themselves.
Wow.
But after brainstorming a bit more, running a few tests, quickly realized if the only solar panel source is if the only energy source is solar panels on the wing, every time you flap, you'll actually change the angle that the solar panels are pointed towards the sun. So solar panels, obviously, if you point towards a light source like the sun, produce a lot more energy than if you point away. When you're flapping, you kind of change that angle all the time. So as you're flapping and you need high energy, you actually get into a state where you start producing less energy, and then you can get into a state where you can't even complete your flap or end up getting a more inefficient system. So we ended up with a design in which the solar panels kind of sit on top of the bird, call it like a solar parachute, which adds drag, but at least in our tests, the drag is less than the energy loss we would have if we put solar panels on the wing, at least the best technology we have so far. And the other factor of that is also the material on the wings has to be lightweight enough that we can keep a small motor size, because the more weight we add on the wings, the more torque requirements we'll have for the motor, especially towards the edge of the wings. So we would start ending up needing a bigger motor if we put solar panels on the wings. And then because you have a bigger motor, you have to produce more energy, so you have to have more solar panels, and that's a never-ending cycle. So Yeah, we ended up just going with like it was like a sort of like a nylon type material for the wings, which was flexible enough to essentially produce lift, but also rigid or like elastic enough that it could survive a few crashes.
Perfect. Yeah. So now the energy bit. Firstly, what are supercapacitors and why do you use them?
Supercapacitors are just capacitors that are super charged. Well, they're just high storage or high capacity capacitors. High storage capacity capacitors. So the reason we use them is that even though we don't have the traditional battery as an energy buffer, you still need a little bit of buffer to act between your solar panels and your load. That's for a couple of reasons. One is to actually get the maximum power out of your solar panels. There's a thing called the maximum power point tracker, which essentially, based on a given load, your solar panel can give you different amount of energy. So it's essentially like you can get more energy out of your solar panels if you connect different size resistors to them, for example. Now, obviously, we're not going to sit there and change resistors on the UAV and match them. So there's a special circuit you can build and use, which is called the maximum power point tracker, which kind of dynamically adjusts your system load. So you always draw the maximum energy out of your solar panels. Without an energy buffer, that system load is going to change and vary a lot. So that energy buffer kind of provides a little bit of stability in the system, so we can actually draw the maximum power point just more reliably. The second is there will obviously, with energy harvesting, it's always going to be an intermittent power domain. So you will run into situations where we end up having a cloud cover, or I don't know, another bird flies over our bird and you get a dip in energy. So we want to have enough energy to at least stabilize flight. So you can go into glide mode, or you can go into like a more stable flight configuration, so you just don't instantly crash once you run into a low power state. You can actually glide and hover and wait to get some energy back and then expend that for flight again.
There's a point that you had mentioned that you're operating under tight constraints. The small supercapacitors only hold the harvested energy, but they're also orders of magnitude less energy dense than a battery.
Yes.
How do you solve that problem?
The main issue, I guess, is that we just need a way to dynamically adjust dynamically adjust flight conditions based on our battery, or not our battery, but our energy harvested. So in a traditional battery situation, if you're running low on battery, you start shutting down your motors and you start essentially triggering warnings and trying to like reduce your throttle and land. In an energy harvesting situation, that low battery state will happen like once every like couple seconds or even more, depending on the state of the system. So we actually developed in a paper that's submitted right now and under review, energy aware flight controller, which essentially can dynamically change your throttle limits and the speed of your motors to adjust for not only present energy harvested, but also kind of a proxy for predicted energy harvesting based on the rate of change of energy you've been accumulating. So it can keep track of how much energy you're accumulating in the past, but also in the very, very recent scope. And based on that, as well as energy consumption over consumption trend over the past couple cycles, it can essentially predict if your throttle needs to be lowered or increased to essentially be in a state where your energy in is always greater than or equal to your energy out. Or if we have enough charge in the supercapacitor, sometimes we can push it as well.
Right. So just to make sure I understand, it's taking into account your past energy usage.
Yeah.
and then using that as information to adjust how much energy it's using. Okay. And in terms of future work, this clearly showed the potential of battery-free UAVs, but how do we make this a practical reality? What are the key steps that you think you would have to follow?
I think a lot of work needs to be done in just more like just creating more energy harvesting based drones, not just battery free UAVs, but also just like battery powered UAVs that have energy harvesting, and starting to rely more on the harvested energy rather than the battery. Because a lot of the times, most energy harvesting drones just use the harvested energy to slowly, very, very slowly charge up the battery again. And it's just a way to extend battery life by like a couple percent. But if we start actually thinking about, okay, how do we incorporate energy harvesting mechanisms into UAVs, and how do we actually solve issues that come up because of incorporating energy harvesting devices like extra weight, or we can't reliably think of like throttle, or like we can't reliably think of control as like a normal UAV or normal robotic system, because now your energy could literally just turn off at any instance. How do you combat that with like your control systems and with your planning and all sort of those things? There's a lot of work that can be done in that area to figure that out. This is a very, very new area. To the best of my knowledge, I don't think there has been another attempt at making a fully battery-free UAV. There was one that was like a battery-free quadcopter, but I think the size of that was insane. It's bigger than this room, and it could only fly for like a couple minutes, and it was quadcopter styles, which meant that any loss in energy whatsoever, it'll just crash. And that's not really something you can solve, because just that's how the design is, right? Because in a quadcopter style or any multi-rotor design, once you lose power to your motors, you lose all control. In a fixed wing or in a flapping wing UAV, if you lose power to your main motors, you can still, if you have like a low power state, you can still move your wings, or at least change the aerodynamic profile of your wings, and just hover or glide in a static configuration without requiring any power. So, there's not a lot of work being done in that field. So just more people looking into that area.
I find it surprising because this is even beyond the sustainability aspect. The very fact that you don't have to recharge your drone is just flying in the air. You don't have to intervene. Don't you find it surprising that this is not getting enough attention?
It's I think it's gotten okay amount of attention for how much work we've done so far. I think once we actually get something flying sustainably for like hours, I think that's the point when, I would start wondering more about like outreach and stuff. But like right now, I think it's okay. I think we're also like trying to actually launch a startup using this technology, and we've gotten pretty good reviews, or pretty good like talks with people at CreateX and other SustainX and similar startup competitions and startup groups here, and that's been helpful. So I think people are usually skeptical at first, but then once I actually explain the idea and what we've done, they usually end up most people see the vision and are excited.
You've also worked on inference-capable battery-free sensor. It's called Protean, and you were one of the researchers behind developing Super Sensor, the hardware part. Could you elaborate more on this?
Sure. So this project was led by one of my colleagues who's graduated now, Abu Bakr. But the idea behind this project was essentially to create a prototyping platform to enable research into battery-free computing more accessible, mostly for like researchers or hobbyists trying to get into the field and learn more about it. So a big thing with battery-free computing is you require a lot of circuitry that you don't require for traditional computing. One basic thing is, for example, you need to be able to keep track of time even after you lose power. So you can lose power in battery-free in a battery-free computer, but you need to be able to tell how long has it been since the last power outage. So there's these things called timekeepers that most battery-free computing-based technologies use. And there's also a few more circuits regarding one, energy harvesting. Battery-free computers typically rely on some sort of energy harvesting mechanism, solar panels, soil-powered harvesting, wind-powered harvesting, thermal, whatever that may be. So you need some sort of input that can actually accept like an energy harvested or energy from a harvester, which is a lot different from a traditional normal power source, because you end up needing something like an MPPT. Then you also need something called like an energy we have a variable energy threshold, but you need some sort of thresholding mechanism to essentially only turn on your computer once you have enough energy to perform a task. Because if you think about it, if, for example, you have a system in which your maximum voltage is 3 volts and you operate and you can operate minimum at 2 volts. What would happen is if you're ever below 2 volts, your system turns off. But the second you get above 2 volts and you've just connected everything normally, your system turns on the second you hit 2 volts. There's a huge current spike because everything's turning on. You do no work and the voltage drops back to like below 2 volts and you get nothing done. And then you get into the cycle again and again and again. So you need a way to disconnect your essentially capacitors or your energy from your computation until you reach a certain voltage threshold where you can actually perform some work. Then you turn on your system, everything boots up, performs the work, shuts down again, and then you wait for the next cycle. So that's like, and the one that we have in Protean is actually a variable threshold. So based on the complexity and based on how many tasks we need to perform, you can actually change what that voltage threshold is. So you can either turn on, if you have a little bit of work to do and it's going to be quick, you can set a lower threshold, turn on sooner, get the work done and just do it. Or if you need a lot of work that needs to be done, you can set a higher threshold, wait longer, but then once you're actually awake, you can get more work done. And then before you go back to sleep. So those are like some of the energy harvesting or battery-free computing circuits that are in the system. But then we actually wanted to create a modular system in which you can not only just snap on different peripherals. If you want to test like facial recognition in a battery-free system, you can literally snap on a camera system to our module. You can snap on microphones, you can snap on ADCs, whatever sensors you want. You can create your own boards and snap those on as well. We can also dynamically turn on and off power to each one of the sensors, either external or internal to the board. So we have load switches to essentially turn on and off everything on the board. So you can go into a super low power state where nothing is getting power, essentially. And the biggest thing is you can also actually replace the microcontroller itself. If you want to develop on a new microcontroller platform, there is this thing called MicroMod from SparkFun, which is essentially, it uses a connector similar to what SSDs use, the M.2 SSDs, the ones that kind of plug into your motherboard. It uses a very similar plug-in type connector, and we've actually made some boards, and SparkFun makes a lot of microprocessor boards that fit that essentially package. And our platform is actually capable of accepting any one of those micromod packages, so you can use whatever microcontroller you want with whatever sensors you want to create whatever battery-free application you want, and all of the extra things you need for battery-free computing are baked into the board. So you have an energy harvester input, you have a variable threshold, you have a timekeeping, and you have load switches to turn on and off everything.
I noticed this common theme between Protean as well as your battery-free UAV about using energy intelligently. You're adapting to the environment. Is that a key factor behind developing battery-free technologies?
Yeah, so once you go battery-free, you have to be a lot more careful with how you use energy because it's a very limited resource at that point. With batteries, it's essentially you'd never have to worry about energy until you have to replace your battery. The only energy consideration is how do we extend battery life, but in the day-to-day, or in the, I should say, like line for coding, you never really worry about, oh, what happens if my code stops executing at this line, or some stuff like that. So yeah, it's a lot. You have to be a lot more nuanced in how you design your hardware, but also your how you write your code to work for a battery-free system.
And now I also want to talk about your most recent project, Phantom Lungs. Where did that come from?
So that was actually a project my advisor did during his PhD, where he created phantom lungs essentially to smoke vapes. So this actually is used for a project we're currently working on. And one we've worked on, my advisor worked on in the past, and we're continuing the work, in which essentially we're trying to monitor e-cigarette usage and try to record data of when a person vapes, as well as bodily signals such as heart rate or fidgeting or other sorts of like biometric markers, to try to predict and give just-in-time interventions to essentially stop people when they're craving rather than after they've already smoked. So currently we're at the stage where we're trying to figure out what are these biomarkers, or not biomarkers, but like more biosignals that can relate to a person craving to smoke, and how do we prevent them from smoking with an intervention.
And explain to us why phantom lungs. I mean, of course, you don't want to test on actual humans, but what's the need for phantom organs? Phantom
organs in general are a pretty good way to test things on humans without needing humans. For example, without a phantom lung, I would have to smoke, I don't know, so many e-cigarettes, more like 10 or 20 to run all the experiments we need for a paper. But also just to design your device, right? It's not even at the experiment stage where you're validating your device, but even when we're designing, how do we actually know when a vape is occurring, and how do we tune our circuits? We need to run a lot of tests and a lot of like different circuits to figure out what works. And doing all of that with a human just adds so much more unreliability to your tests, and so much more variance. With a phantom organ, the idea is that you can replicate the physical system happening. So for example, in a phantom lung, we're not actually like creating a whole lung in which you can like use oxygen and like convert that into like absorb that into a bloodstream or whatever. The only thing our lung is doing is it compresses like a plunger, and then when it's going back to its original state, it kind of sucks in air. That's it. So we're recreating that suction force that you do when you're sucking in from an e-cigarette. And that's what we wanted to capture, and that's what we want to be able to monitor. So a phantom organ is usually very targeted to the specific thing you're trying to sense, and how do you essentially replicate the physics behind that without having to rely on a human to do it all the time.
So what's next for you before you're done with your PhD?
So much. Too much. Mostly working into a new energy harvesting modality, in which we should be able to gather a lot more energy from impacts. That should hopefully be published soon. Very recently, what I was just saying before you stole me for this podcast was working on the smoking paper, and we've created a device that can kind of just snap onto existing e-cigarettes and monitor when users are vaping. and record all of that data and send it to an iPhone. And then more battery-free UAV stuff. And yeah.
Nice.
I also work on some soft robotics.
Rishabh, I wish you the very best in your research. Thank you for taking the time.
Yeah, it was a pleasure being here.